Hi, welcome back to the class again. And today we're going to be on the second lesson of our third module. So the focus now of the third module changed from the mathematics models to the mathematics modeling. We are discussing the modeling process and the methodology. So in previous two modules, you look at other people's models, but start from the module 3, we are going to learn how to build our own model, and how do you know if it's a good or bad model. So in last lesson, we classified the mathematics model in all different categories. For example, we have discrete model if your time steps are integers, or continuous model. The third type, stochastic model, you have probability and the statistics inside your variables. So today we zoom in to the special type, the continuous model, and look at a particular methodology called compartment analysis. So here's the outline. So we're going to first look the scaling of our observation and how we use the scaling to classify the continuous models. And then we further zoom in to look at differential equation as a special type of continuous model. And after this, we go to the methodology, and then we are going to run through an example. So the continuous model in other textbook is also called mathematics physical model, or mathematical physical model, in short, MP. So a MP model is usually defined as an equation that used to look at the dynamic change of a system over the time and the space. So basically, it is focused the most in the physical science objects. That's why it's called mathematical physics model. Specifically, most of those models are either partial differential equation or ordinary differential equations. Of course, it also includes algebraic systems, like what we talked about, the Leslie matrix. So first of all, let's go to the definition of independent variable. Well, that starts from a function. And if you have a function y equal fx, and this x is called the independent variable, and y is called the dependent variable. Well, that sometimes is relative. Let me give you this. And y equal e to the x, and then x is the independent variable, y is the dependent. But you can write this as x equal e to the y, and this is the reverse function equivalent to the y equals logarithmic of x. So now you switch the rule of x and y. So independent variable, dependent variable, in some circumstances are relative. Keep that in mind. But for what we are going to do in this course, unless we tell you differently, most of the time we use the time t as our independent variable. And sometimes you can also use the space x, like the coordinate x, y, z, as independent variable. It really depends what you are talking about. So since the time t is implicitly the independent variable, we sometimes call this as dynamic system. And in this context, sometimes we call it the evolution of the system. That's the same concept. It's the time, the change over time. Well, the second concept, you can call it a dependent variable. But in the dynamic system, we typically call it state variables. Those are the unknown function you are interested to calculate. So this state variable typically is what you can observe. Like you observe the truck is moving, then the state variable of the truck could be its position, its velocity, or its steering direction, so on and so forth. It typically, you have multiple unknown functions in a system. And the system could take the time t alone as the variable, could also take the time t and the space as variable. For example, you want to observe the motion of the hurricane at a particular position. And then you just focus on the center of the hurricane. You could have the t as the particular time, and the x is a vector of x, y, z, is the particular location. So what you are observing is the velocity of the hurricane moving towards which direction. So you can look at those systems. So state variable is the dependent variable of the time, at least. Could be also include the space. Now let's look at an example we are familiar with. You look at the state variable of the AUV or UAV, a robotic vehicle. And typically, you could observe at least 10 dimensional vector. What is the 10? The first S talk about the mode, the modes of the system. The modes of the system is like if we talk about AUV, AUV stands for autonomous underwater vehicle, basically submarine. The mode could be diving, surfacing, and off, on. That's the first variable. That's discrete type. And then you have the position x1, x2, x3 of your local coordinate. And you have the velocity v1, v2, v3. And then you have 3 not accelerations, maybe angles of the pitch angle, yawning angle, and the rolling angle. So that's the 10. But you can get into 14. Like in GPS, we have the time bias and the time drift, and also other change. Anyway, that's the state variables, and we call it unknown functions in the differential equation system. So what is the mathematics model? The narrower definition is the evolution of a state variable over the independent variable. Include the differential equation and the algebraic equation. So, but that's very narrow. Mathematics model also include state transition, graphics, network, and the game theory. There's much more than that. Anyway, when you learn the algebra, you learn that the consistence concept, or say well-defined system. Typically, if you have n variables in algebra, you need n equations to solve it, right? So if the number of independent equations equal the number of the variables, and then we call this system is consistent. The same as a differential equation. The only difference is you are not only talking about a variable, you are talking about unknown functions. And you are not talking about algebraic equations, you talk about differential equations. That's the only difference. So what is the observation scale? The first word we learned is called the scaling. And that's how we define the different mathematics models. So when you observe a system, you can observe the system in the microscope level, and then to treat each individual object as a state variable. So what does that mean? You look at the galaxy, and you can treat each planet like the Mars and the Venus as an individual object. Then you look at the gravitation, and this is called the typical n-body problem. In this n-body problem, you really look at each as an individual. But if you want to consider the whole galaxy of the solar system, or maybe the Milky Way, you are not going to think about each individual star or planet as a body and object. You're going to average, look at the density, look at the distribution, look at the average. If you look in that scope, we're going to call it a macro scope. So basically, there's two types of observation, either in the microscopic components, so you look at each as an individual, or another one, you look at the macroscopic, and then you are not going to look at individuals. You look at average, look at total, and the dynamics. Another example is you look at the ideal gas. You use the word temperature to average the kinetic energy of this system. And you are not looking at each molecule in that level, because the temperature really measures how active all those molecules are bouncing back into each other. So when you deal with the heat equation, you will really deal with the macro level. But in mathematics, we have two different branches of differential equations. One, we call it ordinary differential equation, in short, ODE. That will be your next course after your multivariate calculus. And after you've taken the ODE, the next course is called the PDE. In here, we call it a mathematics physical method, or mathematics method of physics and engineer. That's the name of the title. So you have partial derivatives, we call it PDE.